maybe just a couple of words about my background. I have an industrial background, so not a scientist, but more background on the software engineering and product management. So let's get started. Maybe it's best to actually say a couple of words about the organization I'm coming from. So VTT is, I would say, the National Research Center in Finland, and roughly speaking, 1/3 of our revenue is coming from direct customer engagements, and 1/3 is coming from jointly funded projects, and 1/3 direct government support. So it's kind of like we have a quite nice legging that we can also have some commercial operations, but also we still have also money to do real research and so forth. And the cooperation modes are these kind of customized partnerships, which is the direct interaction with the customers. And then we have a jointly funded project, which can be EU funded, jointly funded, or Finland jointly funded as examples. And then also emphasizing the innovation ecosystems where we can put together partners. And for instance, I'm running the ecosystem in Finland, so we have also a lot of companies that are already in the quantum ecosystem, and we can of course have capability to put things together as we go. Then go into a little bit towards the topic of the material design, and here is something that you may ask that why we have selected material design as one of the hot topics in quantum computing. One of the reasons is that it's actually, in Finland at least, we have the highest usage of supercomputers is actually coming from material design. So I think it's like 2/3 of that. So it's kind of an indication of that there might be some potential also for quantum computing and bringing the advantage of that. Well, the second is that we have actually in-house capabilities of material design, and this slide here is trying to describe that how we could combine these different things together under one roof. One is that we have the material knowledge, the expertise, scientists, and so forth. Also, the application knowledge and process expertise related to that. We have also the tooling needed for material design, which we call here virtual material design concept. It has even a name, VTT proper tool. That is the concept we are using already today. So it's existing classical software methods for material design. And then we have also in-house the quantum computing algorithm expertise. And we are also running actually quantum computers as well at VTT. So all that putting together, we have a kind of pretty much the end-to-end capability to also think what to do with the quantum computing in material design. This is just briefly of the computers we are running. That I'm not saying that VTT as a research institution is necessarily a long-term place to run quantum computers, but we do it anyways. Someone has to do it, so at the moment we do it. And here we have done also quite a lot of work in quantum computers. We have designed the 520 qubit computers jointly with the IQM. IQM is a Finnish quantum computer manufacturer. So we did those jointly, and now we are also upgrading that to actually 54 qubits as we go. It's under testing at the moment, and we believe that we will be up and running and put it into service end of this year. And also mentioning actually that we do take into account also the hybrid computing. So we have actually in Finland we have so-called Lumi supercomputer. Lumi means snow in Finnish, and that is up and running. The supercomputer has been there already years, and it's upgraded all the time. And we have also connected the quantum computers to the Lumi supercomputer already today. So that's part of the concept. But then going to the tiny bit of the we call it VTT proper tune. This is the tooling needed for material design. So it's already today, it's a classical. We have been working for this already in material design, of course, tens of years, but this tooling has been available already, I would say, 5 to 10 years. And it's, we have tens of customers already using the software, and so it's a combination of software, commercial software, but also the VTT software and the libraries. Everything was available open source, commercial, and then our own software put together to have this kind of capability end to end. And of course here, again, saying that one of the key reasons why we believe that there is so much potential is that material design is actually the biggest user of supercomputing time in Finland. The proper tune is it's a quite a complex system which is able to take into account all the aspects of the material design, whether it's a plastic or wood or metal or superconductor. We have a capability of basically build a digital twin for any material. So because this system doesn't actually, is not relying any material, particular material. So it's kind of like a concept where we can build a digitalized material design. So instead of doing lots of testing, manual testing and so forth, we can do it all in a digital way. And of course, to do that digital way, we do need some data points to do some testing for that, get the data points and so forth. But in the end, it's all digital form. And then something that what we have already done, so I would say that we are still in the early phase of putting the quantum computing in real life. And we have this classical VTT property already up and running. We have been using with plenty of customers. So idea is that this is more like I would say evolution instead of revolution, in a sense that in our roadmap we are gradually then bringing the quantum computing accelerators into the concept, into the roadmap, and then making those as advantage. So I would see that the roadmap is something that we try to be all the time in the edge of the technological evolution, and then bringing those items in gradually into the classical system. So everything is sort of a hybrid by design and from the beginning. So there's no like quantum computing only software or quantum computing only material design, but it's all actually mainly classical, and then we are bringing there step by step those quantum computing elements in. And I personally believe that this is actually the way quantum computing is going pretty much everywhere. So it's more like a gradual process which is very much using everything what's already available, the classical methods, and which will be sort of upgraded or brought into the new features in the roadmaps. So we have done a lot of experiments already. So bringing kind of our material guys, our proper tune guys, the tooling guys, and then quantum computing experts together, and training everybody to work together and doing the experiments together. So we have done quite a lot of stuff already, and there is something promising that, in the sense that we can see that maybe you need only like a few dozens of high-quality qubits, for instance, to run pretty much the most important molecules. So we are not necessarily so far about. We are not very close either, but we are not necessarily talking about very big time frames before we can put the quantum computing in use. But it certainly takes at least 2 or 3 years before we see anything concrete. The areas we have been looking at, what might be the most promising for us, using the quantum computing in the material design, those are the 4 boxes on the right. So we are very much working, for instance, protein-based materials. There is a lot of potential there. We are also looking at the energy storage, like battery or energy storage materials, and also actually the semiconductor side as well. So those are the kind of, we have pre-selected or selected some focus domains for us where we want to focus. We can't do everything, and we are probably focusing on these domains. Then just a couple of words about also some other activities. This was a material design, so one of the absolutely focus areas we have. We also have been doing some work in the industrial modeling and simulation, and also the quantum computing communications. And for instance, my job is kind of looking at VTT, the quantum computing applications. So I'm also thinking a little bit that, we can't yet focus only on one domain only, and we are still keep our eyes open that where to find those algorithms, and there's also synergies probably between the different domains and the algorithms there. So it's important also to work on various domains, at least for us as a research institute. And this is a summary. So material science, absolutely, one of the most promising domains of problems, and we are working on that. And this property work we have been doing so far is sort of, I would call it like a science of benefits. We are not yet there. The science of benefits that we could utilize this hybrid classical quantum algorithms, and saying here that this is very much a hybrid approach. And I think that most of the approaches will be hybrid approaches going forward. And then that we as VTT, we are constantly looking, of course, these kind of beneficial opportunities to work together, whether it's a commercial basis or jointly funded basis or ecosystem basis. So this was all from me. Thank you.